Let we learn about Boolean algebra and its postulates as well as their theorems. So how to define your Boolean algebra is, so it's a mathematical structure with a set of operations used in digital circuit design, and it was introduced by mathematician and logician George Boole in the 19th century. Since then it become fundamentals in the design, and we are going to use this for analyzing your digital circuits. So let me learn about what are the operations available in your Boolean algebra. There are various operations available that can define your Boolean algebra, but the basic operation that can form a base of your Boolean algebra is three basic operations: not or your negation operation, conjunction or and operation, disjunction or operation. So now there are various terminologies that we can use in your Boolean algebra, and using various parameters we will define your Boolean algebra, where it includes Boolean variables, Boolean functions, literals, complements, as well as the truth table. So what does mean by Boolean variable? A variable which is used in Boolean algebra, which can store a logical value of 0 or a logical value of 1, are called Boolean variables, and they are used to store either a true value or a false value. Boolean functions, a function of Boolean algebra which can formed by the use of your Boolean operators as well as your Boolean variables, is called a Boolean function. A literal is nothing but a variable in your Boolean algebra is called as a literal. We are going to represent with the alphabets. Now a complement is the one. So the inverse of a Boolean variable is called as a complement. If I am taking a variable which is represented with alphabet letter A and its complement is represented with A bar, the complement of 0 become 1 and the complement of 1 is 0. Next, let me learn about what does mean by a truth table. A truth table contain all the possible values of your logical input variables and its combination of the output variables. So where here we are going to represent that as in your variables in the form of your rows, and the number of rows which are represented in your truth table depends on your how many number of inputs are available in your given function, and the number of columns of your outputs depends on your how many number of functions you are going to derive using the same input variables. Now, so here we have given the three truth tables of your basic operators of not, and or truth table. Now, since NOT gate is having only one input, so we have a possibility of 0 and 1. So hence we have 2 rows, whereas in AND truth table, since we have 2 inputs here, so hence we have your 4 rows. For each row, there was a possibility of your output function is defined. Next, OR truth table also having 2 inputs with in accordance with your output. So now for each row, so we have represented the possible combination that can substituted on your variables with true and false, so or 0 and 1. Now, so this is the table for not truth table and truth table output function, and there are truth table with inputs and outputs. Boolean postulates. So what are the Boolean postulates we are going to use using AND law, OR law, and negation law? So now if I'm going to OR a 0 with a 0, so my output function of OR is 0. 0 OR of 1 is equal to 1, 1 OR of 0 is equal to 1, 1 OR of 1 is equal to 1. So AND loss will give you 0 AND of 0 is 0, 0 AND of 1 is 0, 1 AND of 0 is 0, 1 AND of 1 is 1. Complement of 0 is equal to 1, complement of 1 equal to 0. If A is 0, the complement of A variable is equal to 1. If A equal to 1, the complement of A is A bar is equal to 0. Next, basic identifiers of Boolean algebra. Now, let me replace one of our input with a variable x, and let me apply here laws on this. So by replacing the possible value with a 0 as well as with a 1, XOR of 0 is equal to X, XOR of 1 equal to 1, XOR of X is equal to X, XOR of X bar is equal to 1. So now if I am ORing with a 0, the output obtained from this OR operation is your given variable X. If I am ORing the variable with a logical 1, output of that will become your logical 1. So though you are adding n number of variables with your logical 1, it would give you the output of logic 1. So if I am adding the same variables, or if I am ORing your same variables, so or with n times if I am adding, the output of your OR function will give you the given variable X only. So if I am going to OR a variable with its complement, always gives the output of 1. So now double negation of your X variable always is equal to the given variable X. So X double bar is equal to X. The same manner, so using your AND, so if I am replacing one of the variable is with the X, so X AND of 1 equal to X. Now it depends on the value of X. If X is 0, you will obtain 0. If X is 1, you will obtain 1. So hence X AND of 1 is equal to X and X AND of 0 is equal to 0. X AND of X is equal to, always it is equal to X only. So if I am doing the AND operation between a variable and its complement will give you the 0. Now, let we learn about what are the laws in your Boolean algebra. So, commutative law, x OR of y is equal to y OR of x. So, if we replace your OR operation with an AND operation, the commutative law is defined as, second law of your commutative law is defined as xy is equal to yx. So, x OR of y OR of z is equal to x OR of y OR of z. Associative law of your Boolean algebra, x and of y and of z is equal to x y and of z. So distributive law in your Boolean algebra is defined as x and of y or of z is equal to xy or of xz, x or of yz is equal to x or of y, x or of z. So now or complement of your or of your x and y is equal to x bar and of y bar, x and y whole bar is equal to x bar or of y bar. So this comes under your De Morgan's theorem. So identity law, this law states that the variable would remain unchanged when it is ANDed with a logical 1 or ORed with a logical 0. So x AND of 1 is always equal to the given variable x. So x OR of 0 is equal to x. Idempotent law, this law states that the variable would remain unchanged when it is ANDed and or ORed with itself. So x OR of x is equal to x, x AND of x is equal to x. Complementation law. So this law states that the complement, when you added a variable with its complement, then it would give you the logical one. When you multiply or AND with a variable with its complement, it would give you the logical 0. So x OR of x bar is equal to 1, x and of x bar is equal to 0. So now the double negation law, this law states that whenever a variable with 2 times negation, it would give you the given variable which is x. So x bar whole bar is equal to x only. So these two bars are cancelled, then it would give you the original variable or the reference variable which you have taken. Commutative law. So this law states that the order of the variable, which is not a matter in this law. So though you are doing the OR operation between x or y or of x, it would give you the same result. The same manner in your AND operation between the two variables, x and of y is equal to y and of x. Associative law, according to this law, the order of an operator, it does not matter. So when the priority of the given variables are similar. So now we are doing the OR operation between x OR of y OR of z, which is equal to x OR of y OR of z. So now, so if I am replacing with the AND operation, then the associative law is equal to x and of y or of z, y and of z is equal to x and of y and of z. So distributive law, this law states that ORing your several variables and ANDing the result with the single variable is equal to ANDing the single variable with each of the several variable and then ORing the product. So x and of y or of z, so you can replace with n number of variables in this or term. So y or of z or of x sorry, w or of n. So like that, if we replace those all n variables in this ORing function, it would give you the summation or of your the variable which is ANDed with the several variables. So x and of y or of x and of z. So in the same manner, using your second law of your distributive law, ANDing of several variable and ORing the result with a single variable is equal to ORing that single variable with each of the several variable and then ANDing the product. So XOR of YZ is equal to XOR of Y, XOR of Z in AND of XOR of Z. So absorption law. So using this absorption law, one of the variable is absorbed. So now I have taken x and of x or of y. So here the y variable is absorbed. So after distributing this, x and of x or of x and of y and taken your common variable which is x, so we would obtain the x variable and the y variable, here it is absorbed. So now we obtain here using your distributive law x and of x or of x and of y. So from this two product term, so take your x variable common, then it is 1 or of y. So as 1 or of y is equal to 1, so now let me replace that with the 1. So hence here x and of 1, it become x only. Next, second law of your absorption is XOR of xy is equal to x. Here also let I take your x is common, then it would become x and of 1 or of y. So when it is x and of 1 or of y is equal to 1, so x is ANDed with your logical 1 which is equal to x. So like this, so we obtain the variable x and here the second variable is absorbed. Boolean algebra theorem, the most powerful theorem in your Boolean algebra is De Morgan's theorem. So using this De Morgan's theorem, so let me distribute your functions. So so here it is defined with the two laws, De Morgan's first law and De Morgan's second law. So De Morgan's first law defines that the complement of product of two Boolean variables is equal to the sum of your complement of each Boolean variable. Now here P and of Q whole bar is equal to P bar or of Q bar. So here we replace the possibilities of your P and Q with the true values and false values, and we obtain P and of Q whole bar output functional values, P bar or of Q bar output functional values. For each combination you are obtaining the same functional values. Hence it was proved that so P and of Q whole bar is equal to P bar or of Q bar. The same manner, the second law of your De Morgan's theorem states that the sum of your or of your two Boolean variables is equal to product of the complement of your each Boolean variable. So P or of Q whole bar is equal to P bar and of Q bar. So here we replace all the PQ with the possible trues and false values and we obtain P or of Q whole bar, P bar and of Q bar. So for each input combination, you have your the output functional values of P or of Q whole bar, P bar and of Q bar, Q bar. So we obtained the same functional values. Hence, it was proved that so P or of Q whole bar is equal to P bar and of q1. So these two laws we are going to use for minimizing your Boolean function in Boolean algebra. Thank you.